Good evening, grade 10s. Welcome to topic 2 of year 10 chemistry, chemical bonding. Let's get into it. So here are our learning intention and success criteria. Have a read through, try to do the KS table down here on the side. Don't just copy down the learning intention and success criteria. It's not good for you. I'll pause for a minute so that you can do that. Pause the video, get it done. Okay, now my minute's not quite as long as your minute, so hopefully you got that finished. So your learning intentions there, we want to look at the difference between covalent and ionic bonds, and then make some predictions about the type of bonds in a compound by, again, using our periodic table. So describing what an ion is and providing some examples of monoatomic and polyatomic. Predict the type of bonds by comparing electronegativity. And then what are the properties of ionic and covalent molecules? So a bit of knowledge there. We need to know what is an ion, what are some of those examples, and what do those words mean? What's electronegativity? What properties do these things actually have? And then finally the skill for yourself is, can I use electronegativity to make this prediction? Why are we doing this? Because names and formulas give information beyond just what's inside of a molecule. Good chemistry is about unraveling all these layers. It does have some really great organizational elements in it. So, quick quiz, 6 questions here for you. Some of these refer back to some Year 8, Year 9 knowledge, and some of this refers back to our last video, topic 1. Have a go with them. I'll go through with them in a second. Okay, now if you haven't finished, pause the video, or at least sort of just try each question before I tell you the answer. What is the charge of an electron? An electron, remember, are those little bits whizzing around the outside of an atom. They have a negative charge. What is the charge of an atom's nucleus and why? Well, if the outside, the electrons are negative, then the inside must be positive. They're positive because that's where the protons hang out. How many electrons are in the outer shell of the halogens? Okay, this refers back to last video. Halogens, remember, are column 7 or 17, depending on which naming system you use. They're our chlorine, fluorine, bromine, iodine, all those ene elements. Remember, they're quite poisonous to humans. They have 7 electrons in their outer shell. How many electrons are in the outer shell of the alkali metals? Okay. Now, alkali metals have 1 electron in their outermost shell, and the next layer under it has 8, but there's 1 in that outer shell. Remember, alkali metals are that first column, your sodiums, your lithiums, your potassiums, your ions type elements. How many electrons do they, atoms in this case, want in their outer shells to be stable? Their outer shells to be stable. Okay, hopefully clued in from last lesson. They want 8 in their outer shell. Which element is holding on tighter to its outer electrons, sodium or argon? Now, whenever you're given a question like this, at the very least, take a guess, because you've got a 50-50 chance of getting at least the straightforward answer correct. Now, the one that's holding on tighter is argon. And remember, as we learnt last week, that as you go up in the periodic tables, you go up in the elemental number, they get more protons, and these protons hold on to the electrons tighter and they pull them in closer, and the atom gets smaller. Okay, the size there is a reflection of how strongly those electrons are getting pulled in. Sodium is bigger than argon. Okay, that outer electrons is sort of sitting there, it's like, whatever, hard work. Okay, but argon's got a lot more protons along the way, and it's pulling those extra electrons, even though the electrons are hating on each other, it's pulling them in tighter. Okay, so chemical bonding. When we talk about bonding, we're going to deal with 2 different types mostly. Ionic and covalent. We're going to learn about a third very briefly, but these are our 2 major ones. And the idea behind bonding is that it's about filling up the outer shells with electrons. Atoms will give each other electrons either by sharing or stealing in order to fill up their outer shell. And if an atom has an electron stolen, and that happens to get rid of everything out of its outer shell and just leave a full inner shell left behind, well, they're pretty happy with that too. Okay. Now, there's a great video on my OneDrive, Dogs Teaching Bonding. Have a look at that, please, guys. An ion is formed, remember, so an ion is when something has a charge, when an atom gains or loses an electron. So if it gains an electron, it becomes negative. If it loses an electron, it makes it positive. Now, that sometimes messes with students' heads because they think about getting something as making you positive. But think about like getting bad news. You get bad news, you feel sadder. An atom gets an electron, it gets negative. It doesn't. It's not the basically Benjamin Franklin to blame for this. He named it wrong, and I'll explain that to you in physics. But you have to memorize that when you gain an electron, you have to understand when you gain an electron, something becomes negative. Now, like magnets, if you've played with magnets with the North Pole, South Poles, negatives attract positives and vice versa, and this is what we call an electrostatic attraction. Electro in this case referring to electrons, static because they're not really moving, they're just electrons in one electron in some place and an absence of electrons in another place, causing something to have a positive or a negative charge. Okay. Now, I must have tapped on that previous page. So on your periodic table, go grab it. If you don't have it, pause it, go grab the periodic table and come back. Alright, now you've got your periodic table there. If it's not in your hand, pause it, get it out, put it in your hand. Okay, now you've got your periodic table there in your hand. In our last lesson, we should have identified the number of electrons in the outer shell. We've also identified the size. Atoms want a full shell. That means they want 8 electrons. So what do you think might happen to the atoms on the left-hand side compared to what do you think will happen with the atoms on the right-hand side of your periodic table? Okay, so the left-hand side are your alkaline and alkaline earth metals, and that actually includes the row 3 underneath boron as well. Sorry, not row 3, column 3 under boron as well. What do you think about ones on the right-hand side? Your halogens, some of your non-metals and other things. They're underneath oxygen and underneath nitrogen, etc. Now, what do you think might happen to those atoms? Do they want to get electrons or give away electrons? Okay, now hopefully from thinking about our discussion at the start where we talked about atoms holding on tightly versus loosely with electrons, the ones on the left are going to generally give it away. It's a lot easier for them to just give away those last couple of electrons and fall back to their happy full inner shells. While atoms over on the right, they are holding on pretty tight to the ones that they have, so stealing a couple more, well, that's not too hard for them to do. They can take a couple more just to get up to that full shell. So what I'd like you to do is add the following numbers: plus 1, plus 2, plus 3, plus or minus 4, minus 3, minus 2, minus 1 to those columns. So let me get my pen up here. This is column 1 above hydrogen. This is column 2 above beryllium, column 3 above boron, 4 above carbon, 5 is nitrogen, 6 is oxygen, 7 is fluorine. Now these ones here, they don't matter. They're not going to form any bonding here because they've got a full shell. Okay, that's why they are noble gases. They don't chemically react because they're already pretty happy. So add your plus 1, plus 2, plus 3 to columns 1, 2 and 3, plus minus 4 to column 4, minus 3, minus 2, minus 1 to 5, 6 and 7. Okay. Alright, hopefully you got that done. If not, pause it and give yourself a few more seconds to do it. Now all those big metals in the middle, they don't behave. Some of them have multiple different ions. Like here you've got vanadium, which is a plus 4, but vanadium was here. And then you've got copper here, who's got 3 different versions of an ion because he can't make up his mind. So let's not worry about them. Okay, if you are dealing with any metals in the middle and you're not going to have them for your assignment or for your exam, But if you had to do with any of these for an assignment, just look up what their ion is. Don't worry about trying to remember a rule for any of them. So this is the process. Here's sodium. You can see it's got, happy inner shell 2, next happy level 2 shell with 8, and then just one poor little bugger sitting down and he's lonesome. Off he goes. Now we've got 2 and we've got 8. Fantastic. Chlorine, we've got 2, we've got 8, we've got 7. Oh, he's so close. But if he filled up that last little spot, there's like a little gap. Let me get my pen up. There's a little gap. It's just sitting there. He just needs one more electron, and then he's chockers. Bang! Chlorine 2, 8, 8. That's a chlorine ion. He's right as rain. He's got his 8 electrons. Okay. So that's why we've got chlorine with a minus sign. Remember, we don't write 1 minus. You could if you wanted to, but we don't because we're lazy. Okay, so here's a table for you to fill out. We've provided this worksheet for you on eLearn, and it's also on the booklet if you happen to be using that. Complete the booklet, give it a go with working out the names. We've got some examples of names down here that should let you figure out what these are the names. Remember, metals, positive metals always keep their names, but negative non-metals get an "-ide" on the end. So I'll give you a couple of minutes and I will just jot down a few of these. Go back to my pen. So beryllium here, 2+. It's lost. Nitride, 3. He has gained some electrons because he's become negative. He's gained. He's lost. He's lost. That's a positive, so it'll just be called silver still. That's positive, so it'll just be called tin. He has lost one, become negative, so now he's called chloride. So over here, chloride, not chlorine, but chloride. And nitrogen, nitride. But Be there is going to be kept as beryllium, but I'm not putting that in there. It's a big log for that space with this handwriting. This one has lost 2 electrons, gained 3, gained 1, lost 2, lost 1, and then the total number of electrons. Well, I don't have my periodic table here with me, so let's see. Nitrogen, I'll do nitrogen here because nitrogen is element number 7. Okay, but he's gained 3 extra electrons. Okay, he would normally start with 7, his element 7, so he should have 7, but he's gained an extra 3, so he's got 10. Beryllium is element number 4, but he's lost 2, so he should have 2 electrons. Chlorine is element number 17, but he's gained 1, so he should have 18 electrons. Tin and silver, not sure what their atomic number is off the top of my head, but what you'd have to do for each of them is just find whatever the atomic number is for tin, take off 2. For silver, just take off 1, and you'll have whatever goes into those last 2 columns. I'm sure you guys can figure that out. So, opposites attract when it comes to chemistry. So if 2 elements are nearby, and they're going to have to be different because a tin element, tin will always form that +2. Even say copper with 3 different versions, they'll all be pluses. So it's going to have to be 2 different elements. I'm not going to say that there isn't any, but I don't know of any elements that form a positive and a negative ion. There are some, like carbon can form positive and negative versions of itself, but it doesn't involve ionic bonding. So because ionic stuff is going to involve generally stuff to the left hand side and to the right hand side of the periodic table, you're not really going to have 2 of the same element forming a ionic bond. If it's the same element, like 2 oxygens, 2 hydrogens, 2 carbons, 2 nitrogens, it'll be covalent bonding. Okay, so I'm going to go with, at this level, let's just say if there are 2 different elements, okay, you're going to get some ionic bonding. And what's happening here is that if there are 2 different elements and there's enough energy, an electron will leave one element to jump to the other. Okay, If we take elemental sodium and chlorine gas forms a covalent bond with itself, and we have enough energy, one of the electrons from sodium will leave the sodium and go hang out with the chlorine, and the chlorine will just leave its buddy chlorine all alone. But then, because the sodium is now positive and the chlorine's now negative, they're like, hey, and they bond. They come and stick near each other. They're attracted to each other. That's what we call an ionic molecule. But ionic molecules are kind of hussy-ish. Okay? Let's say there's only one atom of sodium and one atom of chlorine. Well, those two will bond together and they'll just be sitting there. But you never just have one atom. Okay? In a, let's see, sodium is element, what, number 11? So it's about 23-ish grams. So in 23-ish grams, there'll be 6 times 10 to the 23 atoms of sodium. Okay, even 1 gram of sodium is just going to have billions of atoms. Okay? So you're not going to get just one hanging around. There's going to be millions and millions of little buggers hanging around near each other. And same with chlorine gas. You can have a very small amount of chlorine gas, but you're still going to have millions and billions of atoms of chlorine. And so these things all become positives, all the sodiums become positives, all the chlorines become negatives, and they start partnering up together, but they're not happy enough. They like to form lattices of positive, negative, positive, negative, positive, negative, okay? Because even though we stick a positive with a negative, yeah, this stuff here is good, but there's still a little bit negative here. So we could stick another positive here, and then another negative here, Oh, but what off to the side? Well, we could have a negative, yeah, and then we could have another positive, yeah, and it just keeps forming and forming. And this is why ionic compounds make crystals. The stuff that we remember, the copper sulfate we grew in grade 8, okay, that's an ionic compound. Table salt, ionic compound. The potassium permanganate, the sort of long silver, blackish with a bit of purple tint crystals. Okay? They were ionics. And so you end up with something looking like this. So here we have sodium is the purple, chlorine is the green. But every sodium here has an attraction to all the chlorines around it. Like this little chlorine right here in the middle has 1, 2, 3, 4, 5, 6 chlorines that it's 6 sodiums that it's bonding to, because they're just surrounding themselves. And then we end up with this, which is why salt is square, because the lattice that it forms to give it the most amount of positive to negative cancellation is this cubic shape. With our copper sulfate, the proper shape was a what's what I'm looking for? Rhombus, parallelogram shape. Okay, because that's just because the copper and the sulfate makes that kind of slanted over square, or slanted over rectangle, in order to fit everything as close as possible. So ionic bonding, the atoms don't form an electron sharing bond like we will see with covalent bonding in a second, but because they give each other their electrons, the resultant imbalance creates an attraction, and then that allows them to stick together into as an infinitely large molecule as they want. Technically, every salt crystal is one lattice of just continual bonding between all these sodium and chlorine atoms there. If we make a really big salt crystal, and you can actually grow these at home, if you get a salt solution and you suspend a small bit of crystal inside of it, it will slowly dry around. It will accrete on the more and more, and you can grow quite large solid cube salt crystals, and technically they're kind of like one big molecule, because there's no way of saying, oh yeah, like this one here and this one here, yeah, they're bonded together. But these ones here, yeah, they're bonded together, but they just happen to be just attracted enough that they've got to hang out. The bond between these two, let me put pen, the bond between these two and the bond between those two are equally strong. There's no way to say that, yeah, purple one here and green one, yeah, they're the ones that are bonded, and green 2 and purple 2, yeah, they're bonded. We just can't say it. So ionic bonding is kind of not a bond in thinking about two things holding hands, just that everything's kind of attracted to each other in this big coagulated pile. And a great video about forming salt there as well. Have a look at that if you can. Now, this leads forth to another type of ratio, like we saw with chemical balancing, called an ionic ratio. And in an ionic ratio, we have to talk about the charges. The charges must add up to 0. So if we have a positive, we have to have a negative. The charge is 0. So sodium and chlorine, 1 positive, 1 negative, 1 plus 1, plus 1 plus negative 1 equals 0. Done. So that way we know it's balanced. If the charges don't balance, we're going to add some more positives or some more negatives until it's balanced. So let's have a look at some of these. Magnesium chloride. I'm going to do these three. Have a go at home while I'm going through this. First off, always write the ion. Magnesium, second column, 2 plus. Chloride, 7th column, 1 minus. Okay, so I've got a plus 2 and a minus 1. Well, I'm going to need 2 of these. Okay, 2 of those for that. Cool, that'll cancel. We'll have MgCl2. 2. Now let's do sodium and oxygen, because that's what the oxide standing for. Sodium, Na+, oxygen, that's column 6, so that's going to be O2 minus. Okay, well I've got 2 minuses and only 1 positive here, so we can see I'm going to need another positive. So I'm going to have Na2O. Aluminium and oxygen. Aluminium's on the 3rd column. Al 3 plus. Oxygen O2 minus. Okay, so I'm going to need another minus. Okay, that's 4 minuses, 3 plus. That doesn't work. Al3 plus. Okay, that's 6 plus, 2 minuses. Oh hey, that works. So 3 plus, 6 minus. 6 plus, 6 minus. Fantastic. Al2O3. Now, I want you to take a second. I want you to look at these numbers here, the 3s and the 2s, and look at the numbers here, the 2s and the 3s. What do you see? What's the pattern there? You might, if you've watched the video that I've made with the balancing equations, you may have seen this as well there, and you might be cluing on to some structure here. Alright, now all we did was cross multiply. Okay? If I have Al 3 plus O2 minus, well, all I'm doing is I'm cross multiplying, the charges to get Al2O3. Okay, so these sort of patterns and numeracy tricks will help you a little bit. Now, we're not going to do any more monoatomic examples. We're going to look at some polyatomics and then get some practice for you. So, polyatomics. Polyatomics is pretty simple. It just means some compounds, some polyatomic compounds will also be charged. Okay, they're called polyatomic ions. You need to memorize a few of them. There are 6. Okay, so you need to know their names, you'll need to know their formula, and you'll need to know their charge. So a sulfate, S for sulfur, O4 2 minus. Phosphate, P for phosphorus, O4 3 minus. Carbonate is a 2 minus, nitrate with a 1 minus, hydroxide with a 1 minus, and then ammonium has a plus 1. Okay, so when we combine them, they have the exact same rules. So let's combine carbonate and hydrogen. So let's go back. Carbonate we see was CO3 2 minus. CO3 2 minus, and hydrogen is in column 1, so it's plus 1. And all we're going to do is cross multiply the numbers. This is just a 1, so we're going to have 1 CO3 and 2 H2s. We always write the positive first. H2CO3. Alright, here I've given you something slightly more complex. Carbonate, CO3 2 minus, plus sodium, Na plus hydrogen, H plus. Well, the 2 pluses and a 2 minus, well, they're all just going to go together. NaHCO3. Straightforward. If you wrote HNaCO3, also correct. Not a big deal. Technically, if you wrote the negative first, it's still correct, but by convention, we write the positive bit first. Magnesium and nitrate. Mg2 plus. Nitrate, let's go back. NO3 minus. NO3 minus, so we're going to cross multiply. We're going to have 1 that comes down here, 2, now here's the trick bit for this one, Mg1, easy, NO3, now we wouldn't just slap a 2 here, we're going to put 2 in brackets because it's the whole thing doubled. That's the only tricky part about this, in that you can't just go put a 2 at the end, we're going to go N2O6. Technically you could, but it's not fully correct, and I know a lot of you really want to be 100% correct. So just slap it with brackets, chuck a 2 at the end. Now, oops, what's going on there? For you to practice with, I want you to practice combining every cation, every positive thing here, with every negative thing here. So with hydrogen, I want you to write the hydrogen compound with every single one of these anions. Then after you've got all 5 hydrogens, do it with the sodium, every single one of these. There are 25 of them. Pause them, do them in your books. You're going to have to upload a few of these to the e-learning site. Okay, so go pause it and do it now. No, I'm not going to do any more, I just did them on the previous page. Okay, if you need more time, because I'm sure you're fantastic and you smashed all 25 in those 30 seconds I paused, pause the video and complete it in your own time. So that's ionic bonding. Covalent bonding is the opposite. Covalent bonding, instead of electrons being given and taken, they are shared. And mostly these are non-metals, with your carbon, your hydrogen, your oxygen. Most of the stuff in us, like the complex biological molecules that make up us, they're all covalent molecules. Okay? Now note, we don't call it a covalent molecule, we just say molecules. Okay? So they're all covalent bonds, but they're not covalent molecules, we just say molecules. Okay? Now, the big difference between a covalent bond and an ionic bond is a covalent bond shares the electrons. So here's hydrogen, they each only have 1, but they want 2. They want to get to that next level, and so they just share each electron. So this one now has 2 close to it, this one has 2 close to it. Here's methane gas, carbon wants 8, hydrogen wants 2, so this hydrogen now has 2 in its ring, this hydrogen has 2 in its ring, 2, this carbon has 8, so everything's happy. Here's fluorine, again, they've both got 7, they need to get to 8, so they're just going to share 1 with each of each other. Okay, so sometimes it hangs over on one side, sometimes it hangs near the other side, but it's kind of shared there in the middle. And you might be looking at this going, oh yeah, this is your Lewis dot diagrams. Okay, and you do this to work out the bonding between your atoms, or how your atoms will look. So here we'll do a couple together, and then I'll give you O2 to do on your own. It is a bit of a challenge for O2. So we do hydrogen, 1, hydrogen, 1. Okay, they both need to get to 2, so hydrogen, done. And we will draw it as a bond, H bonded to H. Let's do H2O. We've got a H with 1. We've got an oxygen now. Oxygen, remember, if you count on your periodic table, it's in the 6th row, so it's going to have 6 around it, and then we're going to have another H. Okay, and we can see here, this oxygen on this side, we could plug one of these hydrogens in, and we could plug this hydrogen into here. And so that tells us that our shape for water must be O. 1, 2, 3, 4. I'm just going to kind of turn it around a little bit here. H, 1, 2. H, oops, 1, 2. And so our molecule looks like H. H. Okay, that's why water has this kind of bent looking shape here. Now oxygen, give it a shot. Okay, it's going to be a little bit trickier, but I believe you can do it. Alright, so if you still want to give it a go, keep giving it a go. I'm going to start stepping it out a little bit. Oxygen, remember? 1, 2, 3, 4, 5, 6. I'll draw the other oxygen, but I'm going to draw it upside down. I'm going to draw them the other way. 5 and 6. And I'm going to draw a couple of spots. Blank spot, blank spot, blank spot, blank spot. That might help you see what we're about to do here. Okay, now, if you kind of guessed, this one's going to go into here, and this one's going to go into here. They're going to share there, but this one's going to share to here, this one's going to share to here. There are two sets of sharing going on. So oxygen ends up having a double bond. For a real extension, give nitrogen a go. 2 nitrogen atoms, N2. Okay, I'm not going to draw that one at all. Okay, give it a go, see what you get. I keep hitting too low on the thing. There we go. So, in comparison with ionic molecules, covalent molecules don't have electrostatic attraction. There's no areas of negative space and areas of positive that causes them to keep bonding together over really big distances. I mean, you might go, but a salt crystal is not all that big. Sure, to us it's not, but to a single atom, a salt crystal is massive. Okay, remember that you have 10 to the 23 atoms of sodium in about 23 grams of it. So even a 1 microgram, I don't know how much a salt cube weighs, let's say one salt crystal weighs a microgram. Well, in that you would have something like 10 to the 18, so like 10 to the 17, 10 to the 18 atoms of sodium. So that's massive compared to just one. But when we have covalent molecules, there's no electrostatic attraction. And that means things aren't as strong. There's some attractive forces, otherwise like the table that I'm sitting in front of made out of wood would not hold together, because this is not ionic, this is covalent. Okay, there are certainly some attractive forces, that we call them van der Waals and hydrogen bonds, but there's nothing as strong as an electrostatic bond. An electrostatic bond is very strong. And so what that means, if you have a covalent molecule, you can melt it or boil it, okay, because there's not that much force to overcome. In comparison, ionic molecules, those electrostatic bonds are very high, so they are nearly always solid at room temperature. You've got to put a lot more energy into them to make them melt and to make them boil. Like the oxygen gas around us is gas that is a covalent molecule that has boiled off, but it's not like it's burning us alive. I know when I say the word boil, you tend to think of hot water, but boiling, remember, is just the transition from liquid to gas. And so the air around us has boiled off. But, in comparison though, those electrostatic regions are very weak to water, and so they dissolve very easily because it's what we call a polar covalent molecule, which we're about to get to. So, ionic molecules dissolve. nearly all the time. They'll dissolve in water pretty easily. Some of them don't dissolve in water, but will dissolve in other substances, like acetate, for example. But they will generally break down a lot easier compared to covalent molecules. Covalent molecules, once they're sharing their electrons with each other, they don't want to let go, so they don't want to separate. Ionic molecules, yeah, they've shared and they want to stick together, but they really like water, so they'll happily split up and then go their separate ways. So, what's this polar covalent then? So a polar covalent is kind of a combination of the two. It's a covalent molecule that tugs electrons really strongly to one side. And the one that we mostly care about is water, because oxygen is so much bigger than these two hydrogen atoms that this electron pair that they're setting up, this bond that they have, is unequal. It's more tugged to one side. And so it gives oxygen a slight negative side and a slight positive side. Just like an ionic molecule that has a slight positive and a slight negative. But, unlike an ionic molecule, this bond is not going to separate easily. If we separate this bond off, we'd get an acid and a base, which would then start attacking things because it really wanted to have another bond. Now, the root cause of all these different types of bonds is something called electronegativity. Okay? Electronegativity is described as the tendency of an atom to attract a pair of electrons. Okay, a bonding pair of electrons. Fluorine is the most electronegative, and we give it the value 4. There's not some it's not some measurement thing that we've turned around and gone, oh yeah, this is exactly how strong it is. It's a number that we said, nah, it's 4. 4 sounds good. Cesium and francium, in comparison with fluorine, is about 0.7, though francium sometimes gets about 0.8. Definitely put these two numbers, 0.4, so 4.0 and 0.7, on your periodic table. And the patterns I'm about to show you, we're about to talk about, as they move away from fluorine, electronegativity always drops. Okay, so if you go right to left across the period, the negativity will go down. I've written here as you go left to right, so as you start over at the alkalides and you go towards fluorine, electronegativity goes up. As you go down the group, electronegativity goes down. And if you know the difference in electronegativity, you can make predictions. So let's have a look at some numbers here. So you can see here the numbers: 4, 3.5, 3, 2.5, 2, 1.61. Hydrogen's kind of an anomaly up there. If you want to put hydrogen on your thing, feel free. As we go down, 2.0, 1.6, 1.6, 1.8. Some of these would get a little bit weird. Then 2.0, 4.0, 3.0, 2.8, 2.7, 2.2. Continuing to go down. As you go down the metals, 1, 0.9, 0.8, 0.8, 0.8, 0.7. Okay? So the big major thing to think about is, what's this big cluster up here? And then as you go further away, is it close to this? Here are some regions you should know that are generally an okay idea to keep in mind. If your difference is bigger than 1.7, it's ionic. So let's go back here for a second. Sodium, 0.9. Chlorine, 3.0. That's a difference of 2.1. That's very ionic. Fluorine, 4.0. Lithium, 1. So lithium fluoride would be an electronegativity difference of 3. So it's majorly ionic. But if we were to have, say, let's find it. Carbon, hydrogen, difference of 0.4. That's not ionic. Anything under 0.4 is covalent. If it is 0.4 to 1.7, it's more polar covalent. So some of those that are just slightly different but not all that great, they're going to be our polar covalent molecules. You don't need to memorize these numbers specifically, but what I would really heavily suggest, if I tell you something from here and something from here, what will it make? You should be able to tell me it's ionic, because they are very electronegative. They have a very big difference in their electronegativity. If I ask you to predict what's the type of bond between nitrogen and oxygen, well, we can see there the difference would be 0.5. But if you don't remember, it's 0.5, so it means polar covalent. If you say that they're they're right next door to each other, so it's probably going to be a covalent molecule, maybe polar covalent. That's fine. Okay, I'm not expecting you to memorize numbers on this. I am expecting you to go to understand the idea of electronegativity, and that the further things are apart, the more the difference is. The closer they are, the less the difference is, and as such make a prediction about the type of bonding. Okay, so that, I believe, is the end of this, and here is a summary table for you to complete. Definitely do that there. With some of these things like melting points and boiling points, you can just say higher than room temperature, lower than room temperature, or higher than 0 degrees Celsius, less than 0 degrees Celsius. I'm not expecting some sort of major deep analysis there, just for you to clue in about their general states. Alright, hopefully you got all that mostly. Feel free to email me if you've got questions. I know this is a difficult time for all of you, and as I did say in the Collaborate session, this stuff is your lessons on it. Whether you do it by book, you watch the video, you study yourself, you are expected to know these things reasonably well when we come back to school, because we have to pick up where we're up to and continue on with the learning from there. We will not be starting back at topic 1 week 1 and going from it. I'd be happy to sit in at lunchtime and answer questions on it when we return to school, but it is expected that you are keeping on top of the work and asking us questions if you're having trouble with things. Alright guys, take care, have a great week, see you soon.